Hello everyone, welcome back. In this video, let's talk about training single layer neural networks and in particular the perceptron learning rule. So that goes back to the Rosenblatt perceptron that we briefly mentioned in the history of deep learning. So the perceptron is kind of like a model, but thinking about it, the model was already proposed by McCulloch and Pitts, the mathematical model of a neuron in the human brain. So at least it was inspired by this biological neuron, and the perceptron, to be more specific, it's a learning rule for the computational mathematical representation of neural model. So this is now offering us something that can help us find the weights automatically to make classifications, for example. So previously we have seen that how can we manually implement and or functions using specific weights of 1 and a certain threshold. Now with the perceptron we can find automatic weights for different types of problems like classification problems in general. So here's a picture of how that looked like back then. So back then the perceptron was actually a hardware device where people like Frank Rosenblatt here had to plug in and plug out certain cables to reach certain decisions and stuff like that. But we're not in the museum here, so we don't have to go over how that works. Moving on, so I also should highlight, just for correctness, there are multiple perceptron algorithms, and I don't know how many, but there are several variants. Here we are talking about, let's call it the perceptron, so basic version of the perceptron, which is now the commonly known variant. So when we talk about the perceptron, in theory it's a perceptron, one of the classic Rosenblatt perceptrons, but there are multiple ones. We don't have to worry about it here. We just have take the classic one that is commonly known and just refer to it as perceptron for short. Now we have a computational model of a biological neuron here. So for reference, on the left hand side what is shown is the biological neuron, and on the right hand side would be the computational or mathematical representation of that. So the one based on McCulloch and Pitt's idea, and that is also then the model that we are going to use in the perceptron. So the perceptron learning rule would be then learning the parameters of this model. So how does this model work? What we have here are the inputs x1 to xm, and you can think of it as a feature vector. For example, if you think back of the iris dataset, so in this iris dataset we had a tabular dataset where we had sepal length, sepal width, petal width, the 4 features, and then we had number of training examples 1 2 3 4 and so forth. And in this case we had m features where m equals 4. So here is x1 and x2 to m. You can really think of it as a feature vector. For example, a feature vector corresponding to the first training example, and then each feature value gets multiplied by a weight. So you can see each x here goes together with the weight, so they are multiplied to compute the so-called net input, the weighted sum. So this is weighted sum, which you can compute wi times xi, and this is then what we usually use, or we usually use the letter z for the representation, for representing that, to have it more compactly. And then so this is an input here, and then we pass it to the threshold function, and a threshold function is returning this class label. So class label either 0 or 1 depending on the value of z. So if z is smaller than the threshold, then we return the class label 0, and if z is greater than a threshold, we return class label 1. To be more precise, if z is smaller or equal to the threshold, but if we use floating point operations like real value numbers in a computer, then the chance that something is equal is very small, because it could also be equally greater or equal. So in that case we could remove it here. So what I'm trying to say is whether we use 0, smaller than or and greater equal to, or smaller equal to and greater, doesn't really matter. Either way would work because the chance that we have an equal is kind of very small anyways. So in our output, this is either 0 or 1, that is our class label. And now we can then talk about a learning rule for this perceptron that can be used to determine a good threshold and a good value for w, so that we can solve different classification problems, for example classifying flowers in an iris dataset. However, one shortcoming here is that this is only for binary labels, so only 0 and 1. And in an iris dataset, we have 3 flower classes. So if we would want to use the standard perceptron for iris, we would have to simplify this dataset to only 2 flower classes. But we are getting ahead of ourselves here. So also here at the bottom, I just see another equation included. So this is also abbreviating the threshold. So the threshold function based on this threshold theta, if it receives basically the weighted input, so this is the net input, it returns the predicted class label y hat. So y hat, the output, is predicted class label. I will show you how that looks like for a concrete dataset later on. Now here, to recap some of the terminology, I made an overview slide because some of these symbols and words or terms will be used later on when we talk about logistic regression and multi-layered neural networks. So we have the net input, which is just another word for the weighted inputs, and we usually use the symbol or letter Z for denoting that that on the activations. These are values from activation function. So an activation function takes the net input as input, and we use the letter A, and the activation function is sigma, which takes in Z. So this is something that we will be using over and over. And then the output of a model, that is when we apply the threshold to these activations of the last layer of the neural network. And we can, for example, use y hat to denote the predicted label or the output, and f is the threshold function which takes on A. So the flow would be, you can think of it as first computing. If we go from C, so we have Z, it is the weighted net input, so this is computed based on x's and w's, and then we use sigma and activation function to compute these activations, and then we have f to compute the label output. This will become also more clear later on, because right now we have a special case in the perceptron where our activation function is the same as this threshold function. So the perceptron doesn't really have an activation function, they are here in that case synonymous. And in linear regression there is another special case. So some of you probably are already familiar with linear regression. So in linear regression, the activation is equal to the net input, and it's also equal to the output. So in that way, these are two special cases, and it will become more clear. So if we have a linear regression model, if we have then a model here and a linear regression, we would have linear activation or just the weighted sum, and then the output is just a weighted sum. It's our continuous value in a regular neuron. We have usually the steps, we have the weighted sum, so this is our net input, and then we have activation function, and then we have a threshold function, and then this produces our output. However, in the perceptron, these are the same, the sigma and the threshold function, they are just one function, and in linear regression model we don't have these. So the net input is basically our y hat. So there are these special cases, but let's not worry about it too much, because we will be talking about linear regression and logistic regression later on in more detail. So you will see how these concepts of activation functions and thresholds relate to these. Let's focus on perceptron and only worry about the net input and the threshold, where in the bottom here you can again see the summary where we have first weighted inputs as the net input, and then we apply the threshold to return either the 0 or 1 depending on the threshold value on theta. So I want to make one little change to that formula to make things a little bit more convenient. So I just told you that we return 0 if z is smaller or equal to theta threshold, and the output is 1 if z is greater than theta. It's a little bit inconvenient to write it like this. It's not that inconvenient, but for the sake of training the perceptron, it would be more inconvenient. So we will make things a little bit more convenient by rearranging the terms. So we are just now applying the mathematical operation minus theta on both sides. So we are bringing theta here onto the left side, and then we get what we get is we return 0 if z is smaller, if z minus theta is smaller or equal to 0, and we return 1 if z minus theta is greater than 0. So in this way, this is our, I would say, more convenient notation here. And if you think about it like that, you can think of the negative threshold. So this part here, you can think of it as a bias. So this is like a common term in deep learning or also in machine learning. A bias unit, it's a little bit weird to use the term bias because it's a little bit overloaded. There are other types of bias. For example, there's an inductive bias, like this relational inductive bias that we talked about. There's also a fairness bias, and now we have this bias, mathematical bias unit here. There's also a statistical bias if you think of decomposing a loss function into a bias and variance. So it's a bit unfortunate, but in the context of deep learning, if you read the term bias unit, that would be, in this case, this theta. We can treat it as a parameter that will become more clear in a few moments. In this representation, we are now using the bias as a parameter when we compute z. So we set the minus theta to be b. B is short for bias unit, so it's easy to memorize b for bias unit. So we set b equals to this minus theta, and then we compute z. The net input is shown here. So just to recap, what we had before was multiplying the w's and x's. So this is from index 1 to m, and this was our z. Now when we compute z, let's call it z, this includes now our bias unit. So net input is now including the bias unit. If we want to update the figure to reflect that I have drawn here, this b goes now also, this b goes now also into the input, net input. So the net input is really this computation here, and now what we can do is we can also write the activation function, or here the threshold function. So I should have actually used f, but the perceptron is the special case where the threshold function is equal to the activation function. So I can use either sigma or f, doesn't really matter, doesn't here need to be consistent. And so now we can have the 0 here on the right hand side instead of having the minus theta. So this will make more sense from a learning perspective. So in this way, it's easier to parameterize the network if we don't have to learn the threshold here on the right hand side. So it is just easier to write it in code, because then we have a threshold function that just simply checks whether something is greater or smaller than 0. But of course, you can also implement it like shown on the previous slide with the minus theta. It doesn't really matter, but this is also the common notation. And this will be something that you will also encounter when we talk about multi-layer perceptrons, convolutional networks, recurrent networks, and when we use existing code implementation, for example in PyTorch. This is really like the common way also. If you look at recent deep learning papers, so this is, like I said, the common notation that you will find in most modern text, like maybe not in textbooks, because textbooks are usually a few years behind with the trends. But if you look at the modern deep learning literature, you will find that people use this extra notation with additional bias unit here. However, it's slightly inconvenient for mathematical notation compared to a slightly different notation. On the next slide, I will show you how we can modify this even a little bit differently to have the bias as part of the other inputs. Here what I've done now is I'm setting b equals to weight. I call that w0, and this is again our minus theta minus or negative threshold. Now I'm including this bias as a weight. So first, let's maybe start with the figure. If you look at the figure here on the left hand side, what I have done now is I have removed this p here compared to the previous slide, and now have the value 1. This is really like a value, an integer or float number of value 1. And then now I have this w0 as weight. So this is essentially our bias. but I'm writing it as a W because then we can write this notation more compactly. So instead of writing it on the previous slide with index over 1 to M with a W and a B, instead of this I can change this to 0, and then I can get rid of it as slightly more compactly. It's not that interesting to do it like this, but as one advantage of doing it is that we can now use a dot product, just X transpose W. If it wouldn't have the modified version here, what we would have to do is we would have to write it as X transpose W plus B, which is just slightly more work. So the notation here shown would kind of help us to make things a little bit simpler. So why am I telling you this? This notation here on this slide is something you will find in some or most textbooks actually, whereas this in the previous slide I would say that more modern one. I mean, for things like this it might be overkill to use this separate Bayes, so this looks simpler, but when we talk about multi-layer networks, actually this becomes more convenient, and this is also what most frameworks use. Alright, so this is our general framework. And now we are going to take a look at the Perceptron learning rule, so how it actually learns the weights to classify classes. So assume we have a binary classification task. So here we have two classes, these blue dots and yellow or orange squares, and the Perceptron finds the decision boundary to classify these two classes. If the classes are separable, by that I mean if there is a linear decision boundary, I should have maybe said linearly separable. That means there has to exist a decision boundary that can separate these classes perfectly. Then the Perceptron is guaranteed to find it. So here, just looking at it, you may guess that decision 1 you could potentially look like that, and then it will perfectly classify these two classes. So this is a problem here with only two features for simplicity, because if I have more than two features it would be very challenging to draw it in a slide. So in this case we only focus on simple example, and through an animated GIF you can see how the network or Perceptron goes about this task of finding this decision boundary. So starting at a random place, it will basically update the rule in each iteration. So there will be an iteration counter moving up, and it will try to adjust decision boundaries to make them better, basically. So just let's take a look. Actually, I forgot how many iterations there are. There might be 20 or 30 or 40. So you can see it's still making mistakes, and the circles that is shown here, that is indicating which data point is currently looking at. So you can see it's on this black circle. It's moving around because we have shuffled the data set, and then it will look at one training example at a time, and if it finds that there is a misclassification, then it will move decision boundary. So if it's right now, you can see it always finds classes that are already on the correct side of the decision boundary, so no updates are necessary, but it has to find are the ones where it makes mistakes. So if it touches these, see, then it will update. So what you can see here in the lower left corner is the results. It was 49 iterations, so here's the final decision boundary, how it looks like, and you can see it classifies these two classes, say class 0 and class 1, perfectly. Now though, it's only guaranteed to converge if a solution exists. If there is no solution to that, for example, if I have a blue dot that is somewhere here, there would be no decision boundary where you can classify this data set perfectly. And what will happen is if the Perceptron encounters this point, it will move the decision boundary more to this side. So it may even move the decision boundary, let's say, to here, but then all the other points are wrong, so it's moving it back here. But then again, this blue point is wrong and it's going back to the right hand side, so it's always like flipping back and forth. So if data set is not perfectly separable, then it will never stop to converge. Later we will of course learn about algorithms that where this is not the case, where it will always converge to at least some solution, it will at least stop updating, because I mean this is a big issue. If you have a real world data set, classes are really separable by linear decision boundary. There is usually always a case where you can't separate things perfectly, and it would be very annoying if your algorithm makes these big jumps back and forth. So the Adeline algorithm, for example, it will converge even if classes are not linearly separable, and we will learn about this and not in the distant future. But for now, let's stick with the perceptron learning algorithm, just outlining how it learns. So there are these three scenarios. It's the one scenario. So this one scenario is if we make a correct prediction. By that I mean if the predicted label y, the y hat, is equal to the target label. So for that we can also have two scenarios. If y hat is 1 and y is 1, or if predicted label is 0 and the actual label is also 0, then we are correct. Then we don't have to do anything. So if both the predictions of the output are correct, are equal to the target, and and uh, and there are no two scenarios and uh, where things have to be updated. So that is if we are incorrect. So one scenario is where y hat is 0 and y is equal to 1. So in this case, there is a second scenario where we have incorrect decision. So one scenario is where y hat is 0 and y is equal to 1. So in this case, what we do is add the input vector to the weight vector. So we update it like that. And this other scenario is if the output is 1 and target is 0, then we subtract the input vector from this weight vector. So there are two update rules here going on. They are both very similar. We can write this mathematically very compactly as shown here. So here, assume we have a dataset D. This is our training dataset. So we have n data points here from 1 to n. So x our feature vector and y our class labels. So this is our dataset, and now here that's the perceptron learning algorithm. Now how does it work? First we initialize the weights or the weight vectors to zeros. If we have weight vectors, that would be a vector of zeros, and we are assuming the notation where the weight includes the bias. So we don't have to write the bias separately. We could do that, but it would be a little bit more work here. So it would be a little bit more verbose. That's a little bit more compact here. So then we have follow-up here. So for every training epoch, what is an epoch? Epoch means pass over the entire training set. So if I have a training set like shown here, then an epoch would be passing every data point in this data set. So for example, I consider the first data point, I do my computation, then I consider the second one, and so forth until I reach the last one, and then this is one epoch. When I reach this last data point and I have completed one epoch, and then I may go back to the beginning and do another sweep over the data set, that would be then the second epoch, and so forth. So epoch really means pass or iteration over the data set. So this is our outer loop. So for every training epoch in our outer loop, and then the inner loop is for every data point in the dataset. We perform steps A, B, and C. So if we have multiple epochs, that means we can do this multiple times. So we would just go back to the beginning of the training set and do it all over again. So but the interesting part happens now for every data point. Note here, the perceptron processes one data point or one training example at a time. So for every training example, compute the prediction. This is our prediction, and it's computed by computing the weighted sum. This is our net input. So this is input Z, and this is our predicted label. And then we compute the error. So the error is computed by the true label minus the predicted label. Why is that? So if this is 1 and this is y hat is 0, for example, Actually, let's first assume the simple case where we make no error. So if we have 0 and 0, then the error is 0. And then if you look at the row C here, we have the weight update. So C is the weight update. Then the weight update or new weight is the old weight plus the error times the input vector. But if the error is 0, if the prediction is correct here, 0 minus 0 is 0, then we can cancel this term and there is no weight update. If both are 1, then the error is also 0, and then we can also cancel this term. So we can see the weight update only happens if we have an error, if we make a prediction error. And now let's consider the case where we have a 1 and a 0 here. So then the error would be 1 here, so we would have an error of 1 into then we would be adding the weight vector. So if we have the case for predicted label as a 0 and the case for the true label a 1, this is when we are adding something, right? So we are adding the feature vector here. So this is exactly like the case that we have here, y hat is 0 and y is 1. This is the same case here. So if we have the last scenario 0 and 1, then our error is -1, and in this case if this is -1, we are subtracting, right? So w minus x1, so we are subtracting the feature xi, we are subtracting the feature vector which is equal to this case here where we are subtracting the input vector. So here this is really just a mathematical summary of the slide I've shown you before. So what we just have discussed, if this is still complicated, I would I would look at it a little bit more slowly, like step by step, and then maybe don't worry about it too much because we will implement it in code, and after that I think it will be really clear.